future release, I'm not sure when. But for the most part, if you don't care about what values are in the list, then generating them randomly does not actually have that much of a difference than just picking from a smaller subset. You'll shrink the extra noise away anyway.
Yeah, so Leo's response was, yes, we're thinking about that for a future thing, but you still get pretty good random testing even without restricting the set of values to a small set, because the shrinking will kind of throw away the extra information that you get.
The polymorphic function potentially use some magic deriving stuff to prove that you only need to test on certain parameters to generalize to the whole case. That would be fun.
Indeed. For some functions, you could even use parametricity to prove that you only need to test with a small collection of values. That is true. So could you use genetic algorithms to generate test cases instead? I don't know too much about that, so I'm gonna pass on the question and try to go on with getting through the rest of this lecture. But definitely worth thinking about, and maybe somebody is. In fact, testing is a pretty large area, so it would be surprising if nobody had done that.
Is choosing from closed interval?
Choose is choosing from the interval from low to high inclusive.
Inclusive. So that means if I manage to choose high sometime, and then I will choose high forever.
Yeah. So if you manage to choose high at some point, then would you choose high forever, or would you perhaps stop generating at that point? Let's see. I think it would stop generating because that's a strict less than check up above. So you would just get a short example. Okay, were there more questions? Okay. All right. Good. Now let's just finish the example by defining a property, by defining a checker, using for all shrink and our custom generator. And now we don't discard any tests at all, which was the point of the exercise. Yes?
So you use the same shrinking function.
We use the same shrinking function.
But how does that interact with the precondition sorted? Like, do you shrink it?
Excellent question. So the shrinking function doesn't necessarily shrink a sorted list to a sorted list. It probably does, but it might not in a more complicated example. So why does it make sense to use the same shrinking function even when we're using a custom generator? Custom shrinkers are an interesting topic, but of course it doesn't matter here if we discard quite a few of the shrunk tests. Because we shrink them to a non-sorted list, because the total number of shrunk things tends to be pretty small. So it doesn't really matter if we waste a little bit of time during shrinking by the shrinking function generating bad, not well-formed things and then throwing them away. So we just shrink and then test. Okay. So, are we done? No, because this generator is still not as good as it could be. So I leave that for you to think about. Let's look at another precondition. So another example of generating data structures satisfying some condition. So this is the is binary search tree condition, and here is a test for whether a given tree is a binary search tree. Here is an insertion function that might or might not be a good insertion function, I'm not sure. And here is a specification that says if we insert something between the low and high bounds of the tree, and it started out as a binary search tree, then the result of the insertion still will be. Here we are testing it, and we can see that, that we get back a tiny result. So the testing is useful in this case. But we're wasting quite a bit of testing effort. And the reason is that we're throwing away a lot of tests. So that is, if we fix the bug and try running QuickCheck again, it's going to run 20,000 or 2,100 tests and discover that only 1,200 of them pass, and the rest get discarded. So we're not actually doing very effective testing of this property. And your assignment, should you choose to accept it, is to write a generator that produces binary search trees using the example of the sorted lists. Write a generator for well-formed binary search trees that can run tests with no discards. Okay, and that is the end of this lecture a little bit early. Let's see, shall we stop there? Yes, let's stop there, but after questions. So, any questions? Yes?
So, example, if you have a branch, you just chase it. Does QuickCheck guarantee that you're going to check all 3 paths?
Let's see. So does QuickCheck guarantee that you're going to check all the paths in the code? Is that the question? No, it certainly doesn't. And in the testing community, there are lots of people talk about lots of metrics for when testing is good. And one very common metric is code coverage. Code coverage is a pretty basic metric. And that is, knowing that your tests cover the code is not actually telling you all that much, because they aren't necessarily covering all of the paths through the code. They're just covering all the lines of the code. And then people talk about path coverage, and you can still criticize that. So our feeling as QuickCheck developers was that we wanted to put our effort into more powerful testing strategies. More powerful strategies for evaluating the effectiveness of testing, rather than trying to implement things like coverage testing that would be a lot of engineering and not that good anyway. Since you asked, though, let me take a little bit of the extra time that we have to talk about mutation testing. Do we have mutation testing in the tutorial anyplace?
It is in the volume.
Yeah, so you can read about it, but I want to say something about it also. So suppose you have an artifact and a specification of it, and you do some testing, you fix some bugs. Eventually, you get to the point where you can generate 10,000 or 1 million tests, and they all pass. Now, what do you know? Do you know that the artifact is correct? Or that the artifact and the specification correspond, which is really what testing is telling you? No. What you know is that either the artifact and the specification correspond in the way that you hope, or that your tests are badly distributed and they're not finding the counterexamples that are there. Because if you had a badly distributed, if you have a bad enough distribution of tests, you could generate tests, 1 million, 1 billion, and you would never find the counterexamples because they're just not well represented in the tests that you're generating many of. And this is a serious problem in practice. So we need ways of understanding when the tests are giving us good confidence and when they're just successful tests are evidence of bad distributions. Once we know that the distribution is bad, then we can figure out how to tune it. But we need to know that it's bad first. So we need to be able to distinguish between the situation where the tests are badly distributed and the artifact is correct. And the way we distinguish is we break the artifact. In other words, we insert a so-called mutant, or we make a mutant version of either the artifact or the specification in such a way, that is, we alter one or the other in such a way that we're confident that they do not now correspond. Now we run the tests, and if the tests still all succeed, now we know which case we're in. We're in the case that we don't want to be in. On the other hand, if a test fails, then we know that then we know something about the test cases being well distributed. Indeed, if we quickly find a test that fails, then that gives us even more confidence that the tests are distributed in such a way that we're getting good bug finding efficiency. So mutation testing consists of taking the artifact or the specification or both, and manually inserting as many bugs as you can think of, and then running the tests to find out that all of those bugs, that every bug is caught by some test. And so there's a whole part of the QuickCheck story. This is actually something that QuickCheck adds relative to Haskell QuickCheck, is that there's a command line tool that you can run that will take your artifact and specification, run them once through QuickCheck in the usual way to see that the tests all do pass, and then look in your code for comments that look like, here's the beginning of a possible mutant, and here is the mutant text to fill in if you want to exhibit this particular mutant. The QuickCheck tool goes through and one after the other replaces the good text by the mutant text. The reason we do it with comments is that means that the good and mutant text live in the code together, and you can keep adding mutants as you develop the code, so it remains a live collection of tests, and you can keep running. Every time you run QuickCheck, you're getting you're now getting regression tests on all of the bugs that you found earlier that you left in the code as comments. So in the normal development cycle, every time you fix a bug, you leave a mutant, and you put in as many other mutants as you can think of, and then every once in a while you test that your testing is finding all of those. Of course, this is still not a proof that the tests are well enough distributed that they will find bugs that you didn't intentionally insert. But experience suggests, pragmatically, that if you manage to find all of the bugs that you can intentionally think of quickly, that you're getting pretty good, where that's a pragmatic claim, you're getting pretty good testing of bugs that you didn't find. Another way to make that claim pragmatically is to cite examples. The Vellum development, which is part of DeepSpec that we're not talking about so much in this summer school because Steve isn't here, but Steve Zanswick has a project called Vellum that's about building verified optimization passes for LLVM. And in their new round of work on Vellum, they extensively used QuickCheck to debug. So the new version of Vellum has a whole stack of different abstract machines at the high level looking very much like a lambda calculus evaluator, and at the bottom level looking like an LLVM-like interpreter for SSA form instruction sequences, and lots of compilation steps in between them, and very complicated and subtle invariants for the internal steps in this sequence. And the success story is, so they used QuickCheck to debug all of these internal machines, and the success story is when they finally came to proving that all of the compilation steps were correct, the proofs went through the first time. So there were no remaining bugs in that sequence of steps. It's just one example, but it's an indication of the kinds of success stories that are pretty common experience in the Haskell world. That QuickCheck style random testing really does lead to large improvements in code quality.
Short related question. First one, can you highlight what are the guarantees that you provide? In other words, what is the main objective? Does it happen for you to bootstrap as otherwise when you develop more of QuickCheck, does it happen for you to use QuickCheck itself?
Yes, Leo is nodding, so that's something that we're starting to do. So let me repeat the question. So do we use QuickCheck in is it bootstrapped in the sense that we use it to help debug development work on itself? And the answer is yes, we're starting to do that. And the other part of the question again was?
Just to recapitulate, highlight the main guarantees.
Yeah, so QuickCheck is implemented in Coq largely. Some of it is implemented in OCaml, but quite a bit is implemented in Coq, and therefore we have the opportunity to prove things about the implementation. What do we prove? The main property we prove is completeness, well, soundness and completeness of the generators that we construct. So we prove that every generator that we build for you is possibilistically complete. So we don't say anything about probability distributions. That's for you to figure out using collect and so on. But we prove that the values generated by the generator will be all and only the values that satisfy the predicate that you were asked to that you asked QuickCheck to derive the generator from. Okay, so the question was, we put the mutants in comments. Could we instead derive them automatically by looking at GitHub histories or in some other way? That is a great idea that we don't exploit at the moment, but that would be super fun. Another thing that we don't do very much, although we've experimented with it a little bit, is automatically inserting mutants. That turns out to be quite hard to do in a general way, because it's important that any mutants that you insert actually break the property. Because otherwise you spend all of your time on debugging false positives from the mutation testing. So you need a way of breaking things such that you're sure that you're breaking things. In some domains you can do that automatically. And we wrote a paper a few years ago about using random testing for bug finding in information flow monitors. And there we did have some automatic mutation testing. But it's a kind of specialized domain, and it depends on properties of the domain that there's a way to see, all of this large collection of things that I could do automatically will all produce mutants that I will care about.
So can I go back to the previous slide for
Yep.
assignment? So,
This one?
assignment.
Sorry, which?
Assignment, right, for the homework.
The assignment, yes, there.
So maybe we can integrate such a generator by producing always a singleton tree, right?
Yes, okay, so, so the
test of the appropriateness of the generator.
So the question is, looking at this exercise, there's a trivial solution to the exercise, which is a constant generator that always produces the same tree. And that is, of course, strictly speaking, a solution to the exercise. It's not a good solution. And the way you would tell that it's not a good solution is by, for example, mutation testing.
Could you also tell that by proving something like for all binary search trees, there exists a randomness such that a generator...
Yes, that's right. So this is what we do in the QuickCheck implementation. In the QuickCheck implementation is we prove for the generators that we construct automatically that they are complete in the sense that there is a non-zero probability of they're generating every single, or there's some random seed that leads to every single